Today we are going to talk on a technical topic which is related to Boudouard reaction, and our session topic is Boudouard reaction and operational insights in modern blast furnace iron making. In this presentation, we will delve into the thermodynamics of the Boudouard reaction at top of the blast furnace and analyze how gas composition, temperature gradient, and coke behavior influence overall furnace performance. We will also explore key difference between the furnace center and periphery, interpret critical trials data from a high performance blast furnaces, and evaluate dust and gas measurement that reflect real time process health. Though these we aim to extract actionable insight that can help enhance furnace reliability, efficiency, sustainability under diverse operational constraints. Now, we must have undergone through this slide, and now coming to the key observation of this slide is that regarding the Woodward reaction at the furnace top, as we can see at lower temperature between 400 to 500 degrees centigrade, the top gas contain more CO2 and less CO. This happens because the Woodward reaction favors the formation of CO2 at this lower temperature. Now, as we increase the temperature above 700 degrees centigrade, the reaction shift towards producing CO. Once again, I want to say the temperature when it's go above 700 degrees centigrade, the reaction shift towards producing CO. This result in increased CO and minimal CO2 in the top gas. This behavior is due to the reaction being endothermic and highly temperature dependent. That's the overview of how temperature influence the gas composition in this process. Now, coming to the discussion on center versus periphery gas distribution, and this is very important as for furnace practical furnace working is concerned. So let us discuss the temperature and gas distribution difference within the furnace as illustrated by the center versus periphery comparison using red and green color. The red representing the center indicating higher temperatures and higher CO level, typical of the furnace's hot central zone. In contrast, the green dots representing the periphery shows lower temperature and higher CO2 levels. Characteristic of This is the characteristic of cooler zones near the furnace wall where temperature is less. This reflects the temperature gradient and the gas distribution difference within the furnace, highlighting how conditions vary across the cross section. And this is also very important to understand for a operator in real working blast furnace how this Woodward reaction is getting applied. So, coming to now this slide, let us explore the operational implications of Woodward reaction. First, efficient gas utilization is a key. At high CO content at top gas indicates incomplete carbon utilization. As we all know, operators should ensure a balance between raw material quality, permeability, and gas flow to avoid wastage. So, next, temperature control is crucial. A cooler periphery can lead to operational problems like accretion or improper burden descent. At the same time, the lateral moisture going to the wall also is not getting taken care. Adjusting the gas distribution, for example, by tuyere or burden distribution can help equalize temperature. Finally, top gas analysis is most essential, and regularly monitoring CO2 ratio in the top gas is must. Deviation can signal inefficiencies or irregularities such as water ingress or improper coke quality too. Now coming to one of the very important, it may be bit old, but it is a very it addressing a lot of information valuable in nature. It present the results from the trial in 92 and 98 and record production in June 99 and the average of 99 at a high performance furnace, I will say. Starting with the productivity, it ranged from 2.5 in 92 to 3.36 in 99 with average of 2.91. Coke uses vary from 271 kg per ton hot metal in 92 to 317 kg per ton in 99, averaging 316 kg per ton hot metal, while coal users went from 212 kg per ton hot metal to 197 kg per ton hot metal, averaging more than 200 kg per ton hot metal. The theoretical replacement ratio remained stable around 0.79 to 0.85 and uh, SREC if fluctuated between 466 to 486, then average is coming for this is 479 kg per ton hot metal. Top gas utilization was consistent at 48.4 to 48.5, which is really very commanding, with CO2 level ranging from 26.4 to 32.8%, averaging around 30 more than 30%. Flame temperature increased from 2062 in 92 to 2170 in 99, while dust and sludge level so minor variation appraising 8 kg per ton hot metal to 9 kg per ton hot metal respectively. Tuyere velocity increased from 169 meter per second to 185 meter per second, and heat losses rose from 43 gigajoule per hour to 71 gigajoule per hour. Button resistance drops from 608 to 563. Silicon level range from 0.37 to 0.45, averaging 0.43%, and 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 we can see averaging around if silicon as we have said it is around zero point 0.4. Finally, hot metal temperature, if you see 1488 to 1513 over the years, so around 1490 to 1513 is the mostly average. Now coming to the most important aspects is about which focus on the dust and dust component in the top gas at a large furnace. So, as a quick note, the as we can see that amount of top gas dust taken from the blast furnace generally lies between 5 to 15 kg per ton hot metal, and as we introspect the most important graph and its various component, we can say that on x-axis we have a top gas dust measured in kg per ton hot metal ranging from 0 to 14 rather. The y-axis represent correspond to a dust also in kg per ton hot metal up to 14 kg per ton hot metal. We have two key database here. The red square represent the red square represent other components in the dust showing a clear upward trend. The trend line is given by the equation y is equal to 0.79x minus 1.71 with an r square of 0.74, indicating a strong correlation. The black circle represents the carbon content in the dust. This trend line follows y is equal to 0.21x plus 1.71 with an r square of only 0.16, suggesting a weaker correlation compared to other component. This tells us that as the amount of top gas increases, the non-carbon component rise more significantly than carbon. This trend can help identify areas for improving burden distribution, gas flow uniformity, and dust catching system. And finally, in the closing, we will say that Boudouard reaction, a cornerstone of carbon efficiency in iron making, governed heavily by temperature. We observe how center versus periphery differences in the gas composition and chemical profile impact reaction zones and stability. Operational implications such as stop gas CO2 monitoring, temperature equalization, and permeability management were emphasized for process optimization. We also studied real blast furnace performance data showcasing how productivity coequivalence and tuyere velocity evolved over years of optimization. Finally, we examined the dust component analysis of the top gas, revealing how dust trends can serve as a powerful indicator of internal wear, burden behavior, and reaction intensity. In conclusion, optimizing a blast furnace is a multi-variable balancing act from thermochemical reactions to material quality, gas flow, temperature gradient, and by continuing analyzing and adjusting this parameter, we must have to focus on all these parameters. Operators can drive both efficiency and stability in iron making operation.